You pull into a gas station, pump gasoline into your tank, and drive away within minutes. But that fuel started its journey hundreds or thousands of miles away as crude oil extracted from underground reservoirs. At the Motiva Enterprises Port Arthur refinery in Texas, the largest oil refinery in North America, engineers transform 720,000 barrels of crude oil every single day into gasoline, diesel, jet fuel, and dozens of other products. The process involves heating crude to nearly 800 degrees Fahrenheit, separating it into fractions in towers 20 stories tall, cracking heavy molecules under extreme pressure, and blending dozens of components to exact specifications. This is how America's biggest refinery turns black crude oil into the clear gasoline powering your car. The Motiva Port Arthur refinery sits on 1,400 acres along the Gulf Coast in eastern Texas. Originally built in 1903 to process crude from the nearby Spindletop oil boom, it started with just 25 acres, producing 850 barrels per day. Today, it's owned by Saudi Aramco and processes over 100 different types of crude oil, from light sweet Texas oil to heavy sour crude from Canada and the Middle East. The facility employs 1,200 workers, operating around the clock in 12-hour shifts. If you're enjoying this look inside America's industrial processes, hit that subscribe button so you don't miss future videos exploring how everyday products are made. The refining process begins when crude oil arrives by pipeline, tanker ship, or barge. Storage tanks holding millions of gallons feed it steadily to processing units. Before distillation, crude must be desalted because it contains dissolved salts, mainly sodium chloride, plus sediment and water. The desalting unit heats crude to between 200 and 300 degrees Fahrenheit and mixes it with fresh water. Inside the desalter, an electrical field causes water droplets containing dissolved salts to merge and settle to the bottom. The process removes over 95% of salts and suspended solids. After desalting, the clean crude flows to heat exchangers absorbing heat from hot product streams. The partially heated crude then enters a fired furnace where burners heat it to between 650 and 750 degrees Fahrenheit. At Port Arthur, 3 massive crude distillation units operate simultaneously, the largest handling 350,000 barrels per day. Each unit consists of a tall distillation column, typically 150 to 200 feet high. The heated crude enters near the bottom, where most instantly vaporizes into gas. Inside, dozens of horizontal trays at different heights allow vapor to pass upward through liquid flowing downward. As vapors rise through the column, they cool gradually. When each component reaches its condensation temperature, it turns to liquid and collects on a tray. Light gases and gasoline components rise to the top. Middle distillates like kerosene and diesel condense at intermediate heights, and heavy gas oils settle lower. The heaviest material, called atmospheric residue, never vaporizes and drains from the column base. The atmospheric residue advances to vacuum distillation. Under normal pressure, heating this heavy oil above 750 degrees would crack the molecules. The vacuum column operates at pressures below 1 pound per square inch, dramatically lowering boiling points. Vacuum distillation yields vacuum gas oils used for making gasoline and diesel, plus heavy vacuum residue that feeds the delayed coking unit. If you're finding this fascinating, hit that like button to help us keep bringing you these detailed looks. Port Arthur's delayed coking unit, processing 54,000 barrels per day, breaks down heavy molecules. Heavy vacuum residue enters large drums heated to over 900 degrees under pressure. Lighter products vaporize and exit as gases, while solid carbon, called petroleum coke, remains behind. The process uses 2 or more coking drums operating in alternating cycles. While one drum fills with fresh residue for 16 to 24 hours, the other cools and workers cut out the solid coke using high-pressure water jets. The coke is either sold as fuel or further processed. Delayed coking produces naphtha and gas oils that become feedstocks for other refinery units. Fluid catalytic cracking is the primary gasoline-producing unit at Port Arthur. The 81,000 barrel per day FCC cracks heavy gas oils into lighter products. Feed enters a reactor contacting hot catalyst particles at around 1,000 degrees Fahrenheit. Hydrocarbon vapors and spent catalyst exit together into a cyclone separator that captures catalyst while letting product vapors continue to a fractionator. Spent catalyst flows to a regenerator vessel where air burns off carbon deposits at around 1250 degrees. This regeneration restores catalyst activity and provides heat for cracking reactions. Hot, regenerated catalyst continuously circulates back to the reactor. FCC produces high-octane gasoline components, light cycle oils for diesel, and propylene for petrochemicals. Hydrocracking uses hydrogen under extreme conditions. Heavy gas oils enter reactors with catalyst and hydrogen at 2,000 pounds per square inch and around 700 degrees. Hydrogen both cracks large molecules and saturates the fragments. Hydrocracking produces high-quality diesel and jet fuel with very low sulfur. If you're enjoying this detailed walkthrough, give us another like. Hydrotreating removes sulfur, nitrogen, and metals from various streams using hydrogen and catalyst. The process operates between 500 and 800 degrees at 300 to 1,500 pounds per square inch. Modern standards require diesel to contain less than 15 parts per million sulfur. Catalytic reforming boosts octane ratings. Port Arthur operates 2 reformers processing a combined 134,000 barrels per day. The reformers use platinum catalysts at around 1,000 degrees Fahrenheit. Chemical reactions rearrange hydrocarbon molecules, converting straight chains into branched structures, and aromatic rings for high-octane gasoline. Alkylation creates high-octane gasoline components by combining small molecules. Port Arthur's 18,000 barrel per day unit reacts isobutane with light olefins from FCC and coking units. The reaction uses sulfuric or hydrofluoric acid as catalyst at 60 to 100 degrees. The product, called alkylate, has an octane rating exceeding 95. After conversion and treatment, dozens of intermediate streams blend into finished products. Gasoline blending is complex because finished gasoline must meet requirements for octane rating, vapor pressure, sulfur content, and aromatics. Computer programs track every stream's properties and calculate optimal blend recipes. Port Arthur's system combines over 40 components to make multiple gasoline grades simultaneously. Vapor pressure control is critical for environmental and performance reasons. Summer gasoline needs lower vapor pressure to reduce evaporative emissions, while winter blends need higher vapor pressure for cold starts. Refiners adjust blend recipes seasonally and regionally. Quality control labs continuously analyze samples to verify specifications before products ship. Finished products flow to massive storage tanks in the tank farm. Port Arthur has storage capacity exceeding 10 million barrels across hundreds of tanks. Gasoline and light products use floating roof tanks, minimizing vapor space, while heavier products use fixed roof tanks. Tanks connect through an intricate pipeline network with pumps, valves, and meters. From storage, products leave through multiple channels. 3 major pipelines connect directly. Colonial carries products to the East Coast, Explorer serves the Midwest, and Magellan distributes throughout Texas. Tanker trucks fill at loading racks with precise metering systems. Marine terminals along the Gulf allow export to international markets. Beyond transportation fuels, Port Arthur produces specialized products. The facility includes the largest base oil plant in the Western Hemisphere, producing 6 grades of high-quality lubricant base oils. The refinery also produces propylene and cyclohexane for petrochemical manufacturing. Propylene becomes plastics, while cyclohexane converts to nylon. The refinery operates as an integrated system where everything connects. Hydrogen from reformers supplies hydrocracking and hydrotreating units. Steam from waste heat drives turbines producing electricity. Fuel gas from various processes fires furnaces, and sulfur recovered from hydrotreating becomes saleable product. Safety systems blanket the entire facility. Thousands of sensors continuously monitor temperatures, pressures, flow rates, and product qualities. Alarms alert operators, and automatic systems can shut down affected units. Pressure relief valves, flare systems, and fire detection equipment cover every processing area. Environmental controls match the emphasis on safety. Vapor recovery systems capture gasoline vapors during loading. Wastewater treatment removes oil and contaminants before discharge. Sulfur recovery units capture over 99% of sulfur, and flue gas scrubbers clean emissions from furnaces. From crude oil arriving by pipeline to finished gasoline leaving by truck. From 700-degree furnaces to precision blending systems. Every component works together, transforming raw crude into products powering modern transportation. Most drivers never think about the complexity behind filling their gas tanks. Thanks for watching this detailed look inside America's largest refinery. If you enjoyed this video, hit that like button one more time and subscribe to see more manufacturing processes that quietly keep the modern world running. See you next time.
Picture this. A massive container ship longer than 3 football fields, weighing 50,000 tons, worth $200 million when it was built. Now it's worth more dead than alive. Every year, over 1,000 ocean-going ships reach the end of their life. And most of them end up on a beach in India, where an army of workers armed with nothing but cutting torches and sledgehammers tear these giants apart piece by piece. Today, we're going inside the world's largest ship graveyard, where some of America's retired naval vessels and cruise ships meet their final fate. This story begins in Alang, a stretch of beach in Gujarat, India. If you look at satellite images, you'll see something incredible. Dozens of massive ships lined up along the shore like beached whales. This 10-mile beach handles nearly 50% of the world's ship recycling. Over 400 ships per year, the scale is absolutely staggering. But here's the question. Why India? Why do ships from America, Europe, and Asia all end up on this particular beach? The answer changed the global shipping industry forever. Back in the 1970s, shipbreaking happened in developed countries like the United States and Britain. Dry docks, cranes, proper facilities, but it was expensive and slow. Then in 1983, a Kuwaiti tanker owner named Mohammed Hamza had a problem. His ship was too old to operate, but scrapping it conventionally would cost more than the steel was worth. He made a calculated decision: beach the ship at high tide in Alang, wait for low tide, and let Indian workers dismantle it. The labor was cheap, environmental regulations were minimal, and the beach's unique tidal range, reaching 40 feet, meant ships could be driven straight onto shore. It worked, and it changed everything. Today, Alang employs over 50,000 workers across nearly 200 ship-breaking yards. But before we get there, let's follow a ship's final journey. When a ship gets too old, usually after 25 to 30 years of service, operating costs skyrocket. Rust weakens the hull. Engines need constant repairs. Insurance rates climb. Eventually, shipping companies make the calculation: this vessel is worth more as scrap metal than as a working ship. The ship gets sold to a demolition company, often for $5 to $7 million, depending on size and steel prices. Cash buyers in India, Bangladesh, and Pakistan compete for these vessels. Then comes the final voyage, a slow journey toward the beach with a skeleton crew, sometimes just 10 to 15 people managing a ship that once required 50. As the ship approaches Alang, pilots come aboard. These specialists know the tides, the beach gradient, and the exact moment to drive the ship ashore. Timing is everything. At high tide, the captain opens the throttles one last time. The ship accelerates toward the beach at full speed, around 12 to 15 knots. The bow strikes sand. The momentum carries the vessel up the beach. As the tide recedes over the next 6 hours, the ship settles onto the sand, stranded. And this is where it gets wild. Hundreds of workers swarm the ship immediately. They have a tight window because the next high tide comes in 12 hours and they need to secure everything before then. First priority, drain all fluids. Fuel oil, lubricants, hydraulic fluid, anything valuable or hazardous gets pumped out into trucks. Then the real work begins. Workers climb aboard with oxyacetylene cutting torches, massive sledgehammers, and basic hand tools. No cranes, no heavy machinery, just human labor and fire. They start from the top, cutting the superstructure into manageable pieces. Each section of steel plate weighs hundreds or thousands of pounds. Workers use winches and chains to lower pieces down to the beach, where others cut them into smaller chunks. Here's something most people don't realize. Every single piece of that ship has value. The bridge electronics, radar equipment, and navigation systems get salvaged and sold. Brass fixtures, copper wiring, stainless steel railings. Workers systematically strip everything. The engine room is particularly valuable. Massive diesel engines weighing over 100 tons get dismantled piece by piece. These engines often get refurbished and sold to power plants or factories. Propeller shafts made from specialized steel alloys. Generators, pumps, compressors, nothing gets wasted. But the real prize is the steel hull. A large container ship contains 40 to 50,000 tons of steel plate. At current scrap prices around $400 per ton, that's $16 to $20 million worth of raw material. Workers cut the hull into sections roughly 10 feet by 20 feet, each weighing several tons. These plates get loaded onto trucks and transported to rolling mills across India, where they're melted down and reformed into rebar, structural beams, and new steel products. Here's the crazy part. The steel from one large ship provides enough raw material to build housing for a small town. Literally. That 50,000-ton vessel becomes rebar for apartment buildings, beams for factories, and steel for thousands of everyday products. The entire process takes 3 to 6 months depending on the ship's size. Container ships are relatively straightforward. Tankers are more complex because they carried crude oil or chemicals, requiring extensive cleaning before cutting can begin. Navy vessels sometimes contain hazardous materials like asbestos that demand special handling. Alang can handle anything. The largest ship ever broken there was the Nok Nevis, formerly the Yara Viking, the biggest ship ever built. Over 1,500 feet long, 657,000 tons fully loaded. It took workers over a year to completely dismantle. When they finished, there was nothing left but sand where a floating city once stood. But here's where the story gets complicated. Shipbreaking in places like Alang is incredibly dangerous work. Workers operate cutting torches while standing on steel plates. Toxic fumes from burning paint and coatings. The constant risk of sections collapsing unexpectedly. Fires break out regularly when cutting torches ignite residual fuel or gas. International organizations have criticized conditions at Asian shipbreaking yards for decades. The Basel Convention, an international treaty, restricts shipping hazardous waste to developing countries. Some argue end-of-life ships qualify as hazardous waste because they contain asbestos, heavy metals, and toxic coatings. This created controversy in the United States. When the Navy wanted to scrap old vessels, selling them to Asian breakers became politically sensitive. In 2006, the USS Forrestal, a famous aircraft carrier, sparked protests when the Navy sold it for 1 cent to a recycling company that planned to take it to India. The public outcry led to stricter rules. Now the U.S. government generally requires American military vessels to be scrapped in EPA-approved domestic facilities, even though it costs significantly more. But commercial vessels are different. When cruise lines retire ships like Carnival's older vessels or container ships operated by American companies, they often end up in Alang or Chittagong, Bangladesh, another major shipbreaking hub. The economic reality is stark. Breaking a ship in the United States costs $30 to $50 million because of labor rates, environmental compliance, and infrastructure needs. Selling it to an Indian breaker generates $5 to $10 million in revenue instead. That $70 to $80 million difference explains why most ships still head to Asian beaches. But change is coming. Modern facilities in India have started adopting better practices. Some yards now use cranes to lift sections, reducing manual labor, improved safety equipment, better waste management for hazardous materials. The Indian government, facing international pressure, has implemented stricter environmental standards. Ship owners must now provide detailed inventories of hazardous materials before a vessel can be accepted. Workers receive better safety training and equipment. Meanwhile, some developed countries are building modern ship recycling facilities that can compete. A facility in Texas breaks down offshore oil platforms in ships using advanced cutting equipment and strict environmental controls. European companies have opened high-tech yards in Turkey that combine Asian efficiency with Western safety standards. These facilities prove shipbreaking doesn't have to be dangerous, but they also cost significantly more to operate, and the economics still favor Asian yards for most vessel owners. The environmental benefits of ship recycling remain undeniable regardless of location. That 50,000-ton ship would sit as a rotting hulk somewhere, if not recycled. The steel gets a second life instead of requiring new iron ore mining and smelting, which consumes massive energy. Recycling one large ship saves the carbon emissions equivalent to taking 30,000 cars off the road for a year. The metals, electronics, and other materials reclaimed reduce demand for virgin resources. And for communities like Alang, the industry provides livelihoods for tens of thousands of families. Workers earn significantly more than agricultural labor in rural India. The scrap metal feeds India's massive steel industry, providing affordable building materials for construction projects across the country. It's a complex equation: economic opportunity versus worker safety versus environmental concerns versus resource conservation. Innovation continues pushing the industry forward. Some companies are experimenting with robotic cutting systems that can dismantle ships in enclosed facilities, capturing all waste and protecting workers from hazardous exposure. Underwater cutting robots for sections below the waterline. Others are developing mobile shipbreaking facilities, essentially floating dry docks that can break down vessels at sea and sort materials systematically before touching land. From military destroyers to luxury cruise ships, from container vessels to oil tankers, every ship eventually faces the same fate. Some end up in modern facilities with cranes and safety systems, but most still meet their end on a beach in India or Bangladesh, where workers with cutting torches transform floating giants into tomorrow's buildings. So next time you see a massive container ship passing by, remember, that vessel's journey doesn't end when it stops carrying cargo. Somewhere, eventually, it will drive itself onto a beach one last time, where an army of workers will transform it from a ship into the raw materials that build the future, from ocean giant to rebirth as steel. Thanks for watching. Hit that like button and subscribe for more incredible stories of how massive industries work behind the scenes. See you next time.
Picture this: a 22-year-old college dropout working in a woodshed behind his parents' house in Ohio. The year is 1886. He's mixing chemicals, running electrical current through molten compounds, trying to solve a problem that's stumped scientists for decades. His name is Charles Martin Hall. And in 8 months, he's about to make aluminum cheaper than silver, revolutionize manufacturing, and create an industry worth billions. But here's the crazy part. Aluminum was once more valuable than gold. The top of the Washington Monument, finished in 1884, is capped with aluminum because it was the most precious metal available. Napoleon III served his most honored guests on aluminum plates, while everyone else used gold. Extracting aluminum from ore was so expensive that it cost $300 per pound, roughly $15,000 today. Today, we're going inside Alcoa's Massena operations in upstate New York, one of America's oldest continuously operating aluminum smelters. This facility has been transforming electricity into metal since 1903. This is the story of how a college student's woodshed experiment became the massive industrial process that changed the world. Let's start with Charles Martin Hall's breakthrough. In 1886, he discovered that dissolving aluminum oxide in molten cryolite, then running electrical current through it, causes pure aluminum to separate and sink to the bottom. The process seems simple now, but it took years of failed experiments, burnt equipment, and skeptical professors telling him it couldn't be done. Here's what makes the story even more remarkable. On the exact same day, Hall succeeded in Ohio. A French chemist named Hall-Héroult independently discovered the identical process in Paris. Neither knew about the other. Both were 22 years old. Both filed patents within months. The coincidence is so extraordinary that today we call it the Hall-Héroult process, crediting both men equally. Hall's discovery dropped aluminum prices from $300 per pound to just 50 cents within a decade. But turning a woodshed experiment into industrial production required enormous amounts of electricity. And that's where Massena, New York, enters the story. Massena sits on the St. Lawrence River, one of North America's most powerful waterways. In the early 1900s, entrepreneurs recognized that the river's massive flow could generate huge amounts of hydroelectric power, perfect for aluminum smelting, which consumes staggering quantities of electricity. The Pittsburgh Reduction Company, which later became Alcoa, built their Massena smelter in 1903 specifically to access this cheap hydropower. The location was strategic. Close to Canadian power sources, near shipping routes, and positioned where electricity costs made aluminum production economically viable. Today, the Massena operations complex sprawls across hundreds of acres along the river. The facility doesn't mine aluminum ore here. Instead, aluminum oxide, also called alumina, arrives by rail from processing plants in the southern United States and abroad. This white powder is the feedstock that becomes aluminum. The transformation happens in massive buildings called pot lines. These aren't your typical factory floors. We're talking structures several football fields long, filled with hundreds of electrolytic cells arranged in series, each one a precisely controlled chemical reactor operating at extreme temperatures. Each cell, called a pot, is a giant steel shell lined with carbon, roughly 20 feet long. Inside, molten cryolite mixed with alumina sits at 1,760 degrees Fahrenheit. Massive carbon anodes hang down into the molten mixture from above. These anodes, some weighing over a ton each, conduct electricity into the bath. The electrical current flowing through the molten cryolite causes a chemical reaction. Aluminum oxide splits apart. Pure aluminum collects at the bottom as liquid metal. Oxygen combines with the carbon anodes, slowly consuming them and releasing carbon dioxide. The amount of electricity involved is staggering. A single pot line might draw power equivalent to a small city. Massena's smelter consumes roughly 400 megawatts at full capacity. That's enough to power over 300,000 homes. The electricity cost alone represents 40% of aluminum's production cost. This is why aluminum smelters cluster near cheap power sources. Massena benefits from hydroelectric rates that make production economically viable. Without that affordable electricity, the facility couldn't compete with smelters in places like Iceland or the Middle East, where energy is even cheaper. Inside the pot lines, the process runs continuously, 24 hours a day, 7 days a week. You can't just shut down a pot. The molten bath must stay liquid. If it solidifies, the entire cell is destroyed and must be completely rebuilt, a process costing hundreds of thousands of dollars and taking weeks. Workers in protective gear monitor the pots constantly using computerized control systems. Sensors track temperature, electrical resistance, and chemical composition. Automated systems add fresh alumina every few minutes, maintaining the perfect ratio for efficient aluminum production. Every day or two, workers tap each pot to remove the accumulated aluminum. A specialized machine pierces the carbon crust floating on top of the bath, inserts a vacuum tube, and siphons out molten aluminum at over 1,800 degrees Fahrenheit. The glowing metal flows through heated channels into crucibles, large containers that hold several tons. Here's something most people don't realize. It takes 4 to 5 pounds of aluminum oxide to produce 1 pound of aluminum. The oxygen doesn't vanish. It combines with the carbon anodes, which slowly burn away and must be replaced every few weeks. A single pot line can consume hundreds of carbon anodes per year. The molten aluminum from the pots still contains impurities. It goes to the casthouse, where workers further refine and alloy the metal. Furnaces reheat the aluminum, allowing dross and impurities to float to the surface where they're skimmed off. Alloying elements like copper, magnesium, or silicon get added depending on the final product specifications. Then comes casting. Massena produces several forms. Some aluminum gets cast into massive ingots weighing over 20 tons, destined for rolling mills that will flatten them into sheet metal for aircraft, cars, or beverage cans. Other aluminum pours into smaller billets for extrusion into shapes like window frames or structural components. The most common product is the standard 22-pound ingot. Thousands stack in the yard, ready for shipment to manufacturers across North America. Quality control is intense. Samples from every batch undergo chemical analysis and physical testing. Aluminum destined for aerospace applications must meet extraordinary purity standards. Even tiny amounts of contaminants can compromise the metal's strength or corrosion resistance. Alcoa Mecena has modernized dramatically over its 100-plus-year history. Today's pots produce 3 times more aluminum while using less electricity per pound than 80s-era cells. Environmental controls now capture emissions before they reach the atmosphere, meeting strict EPA standards. The workforce has evolved too. Where the facility once employed thousands doing manual labor, today several hundred skilled workers operate largely automated systems. Computer operators monitor dozens of pots from control rooms. Specialized technicians maintain complex equipment. Engineers continuously optimize the process for maximum efficiency. Mecena's strategic importance became clear during World War II, when aluminum demand exploded for aircraft production. The facility ran at maximum capacity, producing metal for B-17 bombers, P-51 fighters, and countless other military applications. Aluminum's lightweight and strength made it irreplaceable for aviation. That wartime boom established aluminum as a fundamental industrial material. Today, global aluminum production exceeds 65 million tons annually. The United States produces about 1 million tons per year, with Mecena contributing a significant portion. But the industry faces challenges: rising electricity costs, competition from cheaper foreign smelters, and environmental concerns about carbon emissions have forced many older U.S. smelters to close. Mecena survives because of hydroelectric power access, skilled workforce, and Alcoa's commitment to U.S. production. The future of Mecena and American aluminum production depends on innovation. Companies are developing new smelting technologies that reduce electricity consumption and eliminate carbon emissions. Using inert anodes instead of carbon could revolutionize the industry by producing pure oxygen as a byproduct instead of carbon dioxide. Recycling also plays a growing role. Aluminum is infinitely recyclable without quality loss. Melting scrap aluminum requires only 5% of the energy needed to produce new aluminum from ore. As recycling rates increase, primary smelters like Mecena must adapt by focusing on high-value applications where recycled metal can't meet specifications. From Charles Martin Hall's woodshed to Mecena's massive pot lines, the aluminum industry has transformed civilization. The metal once more precious than gold now shapes everything from smartphones to skyscrapers, from aircraft to automobiles. Next time you crack open an aluminum can or board an airplane, remember, that metal was once impossibly rare. A young inventor's curiosity and persistence made it abundant. And facilities like Alcoa Mecena continue that tradition, transforming electricity and chemistry into the lightweight metal that defines modern life. From woodshed breakthrough to industrial powerhouse, from precious metal to everyday material, this is Alcoa Mecena. Thanks for watching. Hit that like button and subscribe for more incredible stories about the facilities that built America. See you next time.